Hi all. So today we are going with the lecture number 4 for the continuation of environmental engineering, lecture number 1, part 4. Here you can see we have different water demands. First of all, we have definition of water demand. What is water demand? The water demand is the water required for all of our everyday activities. It includes design of public health engineering schemes. So for this, public health engineer is responsible, and he has to evaluate the amount of water available and the amount of water demanded by the public. In fact, the first study is to consider the demand, and then the second requirement is to find sources to fulfill that demand. Means for designing of any water scheme, it is duty of public health engineer that he has to calculate the water demand and then followed by water supply source. Here we have factors affecting the water demand. What factors could be which can affect the water demand? Number first is size of the city. Number next is extent of industrialization. Number three is type of sewage system. Then climate conditions, cost of water, standard of living. Either it is like a poor area or it is like a big scheme with bungalows. Quality of water, pressure and distribution system, and then type of distribution system. Here we have, you can see that for water, more than 50% of the our calculation is assumption based. Means for any designing of any water supply scheme, most of our calculation are assumption basis. So you have to remember all the assumptions. Unit, what we calculate, which contain a unit of liter per capita per day. LPCD, per capita means per person or a single person. Here we have like we have a diagram that raw water engineering. That what is raw water? The water derived from the natural sources, which actually links with the source and the community. And then we have wastewater, but we are not dealing now wastewater. We will deal in the environmental part two. So right now we are dealing with the raw water engineering. Suppose yearly a person of any city or town consume the water volume is equal to V. As I mentioned you that we have assumption. So we have V volume of water for a person for the year. Then per day, a person of the same city will consume V by 365, means total volume divided by 365 days. For the city, whole population will consume V by 360 into P for population, where P is the population at the end of design life. Here we have a simple flow diagram for the water treatment plant. That first water demand is designed on the basis of average water requirements of the person per day. First, it should be economical. Then we have to forecast the population. Then population always increase, especially in poor countries like where population is increasing, like Pakistan, India, China, Bangladesh. And every unit has to be designed separately. In water demand, we have different terms, but before going to terms, we have defined here natural resources and natural and treatments. So natural resources could be surface water, groundwater, and the rain or precipitation. Raw water, here have your definition that what is raw water? The water derived from the natural resources like river, lakes, ponds, wells, and precipitation. And we have two type of treatments. One is natural treatment, which comes naturally, and then we have artificially what we do through our by using some external resources. So the terms we have annual demand, we have annual average daily demand, and then annual average per capita or population daily demand. So we have to remember because these terms are going to be used in the calculation or numericals. So we have to read it carefully. Number one is annual demand or draft is equal to V. But the complete formula is annual demand upon volume of water required in a year is equal to V. Here we can describe this formula is yearly water demand by a whole city or town. Then we have next formula is annual average daily demand upon volume of water required in a day is equal to V by 365. Then next formula is annual average per capita population or population daily demand is upon volume of water required by per capita per person or population per day is equal to V upon 360 into P, where P is the population at the end of design life or future population. So per person per day water demand. Here we have water demands that what are water demands, are types of water demands. It is very difficult to precisely assess the quantity of water demand demanded by the public since there are many variable factors affecting water consumption. Certain thumb rules and empirical formula are therefore generally used to assess this quantity. So in water demand, we have type of water demand like we have domestic demand, industrial demand, commercial or institutional demand, public utilities, theft or leakages, and then fire demand. So we have these various types of demand, which is divided into below classes, which I mentioned you around six classes. Domestic demand contain cooking, bathing, washing. Industrial demand maybe paper industry, leather industry, or rubber industry, or any industry. Commercial or institutional demand contain schools and offices are and corporate offices. Then public utilities are parks, markets, toilets, hotels, clubs, and other sources. Theft or leakage contain what is required to compensate losses in waste and thefts. And then we have fire demand because in case of any fire in a city or town, we need bulk amount of water for extinguish that fire. So we have a different category, a different class for the fire demand. Unit, as I mentioned you, that we have liters per capita per day, LPCD. The formula for LPCD is equal to total yearly water requirements of a community or population upon 365 into design population. Means how much design population means how much population living in that city or town. Water demand we have we have average because after different researchers are design person or public health people, they design every domestic water consumption. For this we have what domestic water demand. So most means generally if anybody asks you during the interview or you if you have exam, you if you somebody asks you okay what maybe the water in liters for a person. So you have to answer him simply that 135 liters. What is the breakage of this 135? Drinking, it means a human drinks of 5 liters of water in a day. And for cooking, 5 liters per day. For bathing, 55 liters. Washing of clothes, 20. liters. Washing of utensils are 10 liter. Washing and cleaning of houses and residence 10 liter. Flushing latrines or toilets are 30 liters. So 30 liters. So we have cumulative of 135 liters. Here we have uh, two type of terms. One is HIG and other is LIG. HIG is high income group, which are mostly the high societies, like big bungalows or disassociated societies. So they use much more water because they have high standard of living, lands and big houses. So they use 200 LPCD, means they use 200 liters per day. And one is LIG, means low income group, which is low salary, low standard of living. They use 135 liters per day. Here we have a separate slide for this, that demand type, low income families and high income families. For domestic, we have 135, and high income 200. For industrial, 70 liters per day, and for high income, same 70. Public utilities are same 10-10, and theft or leakages are 55. So in total, low income families, they consume 270 liters per day, and high income families, they use 335 liters per capita per day. So 50 to 60% of our total water consumption utilized for the domestic use, 20 to 25% of the total water consumption utilized for the industrial or commercial use, 5 to 10% of the total water or 10 liters per capita per day of the total water consumption utilized for the public use, and 15 to 20% or 55 liter per capita per day of the total water is calculated for the leakages and thefts. Here we have formula that for fire demand we have separate formula. So empirical formula for fire demand, the researchers are environmentalists have to much studies such as case studies and finally given these empirical formula. First one is Kuchling formula, second one is Buston's formula, and third one is Freeman's formula. In Kuchling formula, we have Q is equal to 3182 under root P, where Q is in liter per minute and P is population in thousands. We have a little small example for that. If a city has population of P of around 1000, not 1000, but it is 100,000. We have, if a population of a city, a population with 100,000 of liter, then how we will calculate the amount of water? So we have formula. We have to put the values in formula. P is equal to 100,000 upon 1000 is equal to, because we have to change this 100,000. Therefore, Q is equal to 3182 under root 100. We have put the value inside under root. So Q is equal to 31820 liter per minute. Number two, sorry, is Buster formula. Q is equal to 5663 under root P, where Q is in liter per minute, and same similarly like the previous, P is population in thousand. Number third is Freeman's formula, which is Q is equal to 1136 into P upon 5 plus 10. Same, where Q is in liter per minute and P is the population in thousand. Here we have a water demand diagram, that we have maximum daily water demand, MDD, every daily water requirements for a person. Here on vertical axis we have discharge, and on horizontal axis we have time. So you can see that we have 12 months of a year. You can see that water demand in, for example, this is for the what country, like low income countries like India and Pakistan and Bangladesh. So we have much more use of water in the July, because in July we have uh, much more consumption of water due to because in this time in July it is a peak of temperature. So people they use water for the washing or bathing, and we have very low consumption in January and December. And here we have maximum hourly demand, that in which hour we have maximum water demand. You can see that we have different times like 12:30 or 3 we have this night, then again night. Then you can see that in the early morning, because in early morning uh, everybody, especially the sit downs or cities which have much office areas or schools or something. So in the morning, everybody wants to go on his job. So we have much more consumption of water. Means around 6 to 9 a.m. we have much more demand. After that, this consumption is less or decreased. Then again, office people and kids they come back. So at during the 12 and 3 p.m. it consumption increase, and then finally this is time of sleeping. 3 to 6 p.m. is time of sleeping, so water demand again decreased. Here we have formulas. Q is equal to px, where p is population. Population is given not in thousands. X is water in LPCD. Q is average daily demand of water. Then Q is equal to px. Here we have three formulas which will be used during our numericals, that maximum daily demand MDD is equal to 1.8 Q, maximum hourly demand MHD is equal to 1.5 MDD. And what is the relation between both maximum daily demand and MHD? We have Q is equal to 1.5 MDD. So Q is equal to, just we have to put the formula, then Q is equal to 1.5 into 1.8 Q. So finally Q is equal to 2.7 Q. So in next lecture we will solve this problem. Hope you like the lecture. Thanks for watching. We will meet with the lecture number 5. Thanks for watching.